apart from my
Yes,
Australian accent. Can you hear me okay?
I can hear you. Thank you.
Okay, fantastic. So if you have any questions, feel free to interrupt, because I can't see everybody's faces while I'm giving the presentation. So don't be shy. What I'm going to share is just some performance testing that we did with distributed training on Kubernetes with TensorFlow. And this is a piece of a presentation that I gave at KubeCon, but I think you'll find it very interesting. So as David mentioned, a lot of folks are looking to run ML workloads on Kubernetes, and the SIG is really about that, doing it on OpenShift, doing it on Kubernetes. So one of the things that this work came out of was several months ago, about 8 months ago, the Microsoft research team came to the container team over at Microsoft Azure and said, is there any way you can give us some of your expertise in running Kubernetes and help us understand why we're having performance issues when we try and scale these distributed, training these distributed models on Kubernetes. So I went over and sat with the MSR team for several weeks, and we went through all the scenarios, and this is just the output of that work. So hopefully you'll find some of it interesting. And at the end, there's some future work that we're also doing in this space. So before we get into it, most people say, well, what were you testing on? So you could take this and test it on any cloud and any bare metal setup that you have. What we do here is we've just documented the exact VMs specs that we have for the workers and for the parameter servers, the type of GPUs we have, the type of the version of Kubernetes, all the parameters that we have for the actual test environment. And we're just using, I'm not sure if everybody's aware, we're actually just using the upstream TensorFlow benchmark scripts to actually run these test frameworks against different models. So it's all there for you if you want to go and replicate this and test it yourself. The data set that we're using is ImageNet, which is a real data set, not synthetic. So there's the parameters of the setup environment. So what we did first was we actually didn't do any distribution. We just wanted to do a single node with multi-GPU and just have a look at a baseline at what a model, how a model could be trained and how fast we could actually process images per second out of that ImageNet data set. So you can see here that 1, 2, and 4, we pretty much get linear scalability, and we made sure that all the GPUs were indeed saturated when we were doing those tests. So that gave us a fairly good baseline of what we could do with ResNet 50, batch size 64, running images per second there. So that was a standard. We get linear scaling, because what we wanted to see is in a distributed fashion, did we still get linear scaling, or did that break down? So when we go over to distributed, we started with 1 parameter server and 2 workers. We had async variable updates. So these are all parameters that you can tune inside TensorFlow when you set things up. Using the CPU as a local parameter device, we had each worker pod had its own dedicated host. So we didn't have any contention between parameter servers and worker nodes. So it was pretty much 3 VMs, 1 parameter server and 2 workers, each with a pod for their respective services that we're hosting. We had the variable update mode set to parameter server, and we were using gRPC as the network protocol. Now, what you see here is a single pod training with 4 GPUs and distributed training. So the blue is the numbers that we actually saw with a single pod on a single node, essentially. And then when we scaled it. So these are across the different models: GoogleNet, Inception v3, ResNet 50, ResNet 152, and VGG16. So you can see GoogleNet actually gets fairly good scaling. As you scale out, you get fairly linear scaling. Here's 4 GPUs, here's 8 on 2 machines. You can see that the factor gets a little bit less depending on the model. And for VGG16 in particular, it actually gets worse. So using distributed training with VGG model is actually worse than using a single machine. So this was kind of interesting to us, just to kind of get the data and take a look at how we could dig in and what was actually causing those bottlenecks and understand that. So what we came to find was we took a look at network, we took a look at disk, we took a look at different network configurations that we could do. But really it came down to the compute versus bandwidth ratio. And really when it goes to setting up a parameter server, the bottleneck of the whole system is how fast that parameter server can process the gradient changes and redistribute them to the nodes. And that is actually basically on the network. Although different models have different networks. So computation costs relative to AlexNet, how much computation costs we have for these different models, and across training speed up of 2 nodes versus a single node. So Google Net down in the bottom right here, you get 1.86. So obviously, as a public cloud provider, or anybody who's concerned with costs, if people are paying for 2 nodes and they're using distributed TensorFlow, we want them to get, pretty much linear scaling as they pay for more compute. And with GoogleNet, you can kind of get the closest, but really the average here is about 1.6 at best, and at worst 0.63. So this is just some things to keep in mind as you look at distributed training, because what was a surprise to me was, as an operator of Kubernetes for many years, just throw more hardware at the problem, add more nodes, and surely your results will be better. And that is true to a certain extent, but not the extent that you would think. Now, just some observations that we jotted down was it really depends on the model and network bandwidth in particular. So we had non-specialized network hardware and specialized network hardware. So really what that boiled down to was 10 gig NICs on the VMs, or InfiniBand on the VMs, and how much bandwidth we could consume. GPUs are not fully saturated on the worker node. So even when we scaled it out, we couldn't actually reach full GPU saturation. And it's likely due to the gradients, the batches, and then being redistributed, that the GPUs could never hit full saturation. We could do it with those models on single node systems. Suboptimal performance, so GPUs starved most of the time. There wasn't anything for them to do. We actually tried doing a number of different PS server configurations. So running on the same node as the pods actually seemed to create worse performance. And then we tried to do multiple PS servers and understand whether, if we had multiple parameter servers, whether we would actually get better distribution of those workloads. We also tried synchronous and asynchronous variable updates, but what we actually published in those previous slides was best case that we actually found. So really that got us asking what we can do better. So we went out and we were rerunning a lot of these tests today. Results yet to be published, but before we went into KubeCon, about a week before, Uber released Horavadh, which is an open source distributed learning framework for TensorFlow. So if you've already got your models written in TensorFlow, there's no extra work that you have to do. Horavadh simply shims in. Now this is taken from the Horavadh docs specifically, but really what you can do is enabling different batch sizes here really get linear scaling. So distributed TensorFlow gets this, Horavadh will get that with TCP, and obviously with RDMA you can get a little bit more. And they also publish the ideal linear scalability here. So really what you can see is with larger batch sizes in a distributed training here on Kubernetes, you can actually get closer to linear scaling with Horavadh. Now, it's a standalone Python package if you're not familiar with it, and it's seamlessly installed. Now, it uses Nickel, and Nickel is intra-node GPU communication. And basically, really what you're doing here is distributing the parameter server to the GPUs. So you basically have a completely distributed parameter server rather than a single pod or a single entity responsible for processing the gradients and distributing them to all the nodes. There's Nickel v2 as well, and Nickel v2 is inter-node. So the number of nodes, you can have all the GPUs communicating those parameters and gradients with one another without having to go through a single head in a parameter server. MPI for worker discovery, so there's a reduction in coordination there, and Tensor Fusion. So this is just a way that we can start to look at using TensorFlow, and there are other tools out there that we might be able to achieve linear scaling, because when we go to these distributed models on distributed compute and in the cloud, we really want to get as close to linear scaling as possible. That's what we're going for here. So there's another paper out there that's also of interest. So it's deep gradient compression. So there's been analysis on those gradients. So that's as the model's being changed, the delta in the parameters that get distributed back up to the parameter server, they're actually turn out to be fairly redundant. 99.9% of the gradient exchange is actually redundant. So the purpose of this gradient compression is really to get your parameters, your gradients actually down to reasonable sizes before shooting them down on the wire, right? So you're going from 100 meg or 500 meg down to less than a meg for most of this. So another way that we can actually take care of scaling, and as we go, obviously we only had 2 nodes, but people may want hundreds or thousands of worker nodes. But this really allows you to scale in our testing on 1 gig Ethernet VMs. So you don't need specialist hardware and you don't need large NICs in your VMs. So another interesting fact there. Now, just some other tools that we actually have out there. So there is a deep learning, open source deep learning workspace that we publish. Now, this is akin to a very point and click experience. And we're also working with Kubeflow, as David mentioned. But the DL workspace predates Kubeflow a little bit. So if you're interested, you can shoot over here. It's open source. You can take a look. But that's very UI driven, supposed to give data scientists access to a bunch of different frameworks: TensorFlow, PyTorch, Spark, and a very lightweight way to get entry. There's a couple of other things that we're working on. So FreeFlow CI plugin. So this may be of interest in this forum, but you're really leveraging shared memory and RDMA to improve network performance. So we've published a CNI plugin called FreeFlow that allows you to get a little bit more out of the networking stack when using TensorFlow. So that's deployed as a daemon set. And there's a custom CRI and scheduler that we've also released. Let me just pop over. So these are both open source toolkits that you can go and take a look. So if you want to run Spark in this DL workspace, there's a document on how to do that and set this up. And this will run on any Kubernetes cluster, anywhere on any platform, just using Kubernetes abstractions. Finally, just this week, we repackaged and open sourced a custom CRI to give us more granularity and GPU constraints, and a custom scheduler for Kubernetes to be able to bubble these GPU constraints, not only how many GPUs you have, but different vectors inside those GPUs. So feel free to go and pick that up, take a look at it, and contribute. At this point, I will open it up to any questions.
Let's see.
I was listening to this and wondering, some of the stuff you just presented reminds me a little bit of how, you know, the old MapReduce formalism got its traction, where it's going to be, you know, opinionated. It's like, we're going to focus purely on stuff that actually scales well. And so I'm kind of, I guess, like in terms of Kubeflow direction and other stuff like that, I wonder if this indicates we should be fairly opinionated as to what kinds of implementations we support. Sorry, I also have a bit of flu here. But you know, we're not gonna provide implementations that don't come close to linear scalability, just because we don't want people to be surprised.
Yeah, you know, I think that's a really excellent point, Eric. I won't, like, I'm not so hardcore in opinionation. This is my opinion, so not as a Kubeflow person, just as an ML person. I'm not so hardcore in implementation that I will literally block people from running stuff that is going to have a bad time. But I think it behooves us to really double and triple down and make sure that people are aware that, you know, to the extent possible, hey, do this, or you may not scale linearly, right? And it's exactly the kind of stuff that research that Lachlan has provided here and things like that will help people be aware of it. But second, you know, it will help us, you know, indicate like, hey, if you want to get linear performance here, you really need to be including, you know, a higher level MPI framework or something along those lines. So, you know, I'm all for leveraging this kind of research and either putting it into docs or making it the defaults, you know, things like that.
Yeah, absolutely. And I think, you know, even upstream in TensorFlow specific, now that these performance benchmarks are there and people are starting to process the numbers, the TensorFlow community as a whole is doing a lot. As you mentioned, it's very akin to MapReduce. Once you start to see the numbers there, people are actually taking action to to get this closer to linear scaling, because it's a surprise to most people that it is not currently. So we're continuing that research and expect to see a little bit more. And I can add the slides to the talk. And if you're interested in chatting with either myself or the Microsoft research team that I worked on this with, happy to discuss.
Perfect. Thanks, Lachlan. This research is pretty bloody awesome and really helpful. And thank you for sharing it today.